Chapter 9, Segment 1, Theories of Bonding and Structure. So in essence, we're going to be looking at more ways of looking at bonding. So in this chapter, we're going to look at how to draw the 5 basic molecular geometries, look at Vesper, how to use Vesper model to predict the shape of the molecules and ions. We'll understand the influence of shape on the polarity, so we'll talk about dipole moment some more. And then we'll explore how valence bond theory explains bonding. And we'll get into hybridizations and look at valence bond theory. And then we'll learn to use orbital diagrams and hybridization to describe the nature of multiple bonds. We'll look at orbital diagrams and hybridization to describe the multiple bonds, and then examine molecular orbital theory and use it to explain the nature of diatomic molecules. We'll then compare resonance structures to delocalized molecular orbitals and explain bonding in and physical properties of solids using band theory. And then finally, we'll explore allotropes of nonmetals using hybridization and valence bond theory. So it sounds like a lot of repetitive stuff, a lot of hybridization and molecular bonding, this type of thing. So again, more bonding theory, kind of building off of Chapter 8. So molecular structures then, these are molecules containing 3 or more atoms. They could have different shapes. We typically forget that most of these things are going to be 3-dimensional, and we live in a 3-dimensional world, and that includes our molecules. The shapes then are made of 5 basic geometrical structures. Okay, so we're going to start with 5 basic geometries, and then look at how we can break that down. So shapes classified according to the number of electron domains they contain around the central atom. So we'll be focusing on the central atom and looking at these electron domains. And what we mean is are they bonding, non-bonding? Are they paired up? Are they forming pairs? What are they doing there? And based on those details, it will give us an idea of what the molecule would look like in 3 dimension. So we're going to base a lot of this on what's called Vesper theory, VSEPR, which is valence shell electron pair repulsion. So remember, we can have a plus 1/2 and a minus 1/2. In other words, we can put 2 electrons in the same orbital as long as they're spinning in opposite directions. Once we have those 2 electrons, that's our pair, they now will have a repulsion component against other electrons. All right, so these electrons are going to want to get as far away from other pairs as they possibly can. So it's a simple model using the electron domain concept. So there's 2 types of electron domains. There's going to be bonding domains, where the pairs are going to be involved in the bond, and of course the non-bonding domains. And these are going to be our lone pairs. All electrons in single, double, or triple bonds are considered to be in the same electron domain. So whether it's a single bond, a double bond, or a triple bond. Now remember, what that implication is that if it's a single bond, there's 2 electrons, double will be 4, and then of course a triple will be 6. So all of them would be considered to be in the same domain for that bond. Now it's a simple theory for predicting the shape. So here's what we're going to take advantage of. Negative electrons repel each other very strongly. That means that they want to get as far away from each other as they possibly can. So if I'm looking at a 2D surface, then that means 180 degrees, right? Would be as far away as they can get from each other. If I have other pairs there and I introduce another pair, now it's going to be possibly 120. And then we introduce another pair, you would think it would be 90, but actually we can flip that into 3 dimensions and we can get to about 110. Excuse me, 110, not 1010. That makes no sense. All right. The reason why they're going to do this is to minimize the repulsion between the pairs. So electron pairs then are arranged to have the lowest possible potential energy. So again, we want to get them away from each other. The closer they are to each other, the more they'll repel. The more they repel, the more energy there is. So some assumptions. Bonds are shared pairs of electrons, okay, which means that's kind of true for covalent bonds. We're also going to say the central atom will have 2, 3, 4, 5, or 6 pairs of electrons in its valence shell. Okay, so it can either have 2, 3, 4, 5, or 6. The model includes central atoms that have incomplete octets, complete octets, extended octets. Now we saw examples of all of those in the previous chapter. The electron domains will be lone electron pairs, single bonds, double bonds, and triple bonds. All count as just one electron domain. So if we look at just having two domains, right, then the shape is going to be 180 degrees from each other, and we call that linear. If we have three domains, now remember we're getting as far away from each other as we can, so that's going to give us 120 degrees. It's still going to be a planar molecule. And at that point we say it's trigonal planar. It's got that Mercedes-Benz look if you put a circle around it. Now once we get to 4 electron domains, the electrons are going to pop, is the way I like to think about it. They're going to pop out of the 2D and into the 3D, and we're going to form a tetrahedral. And so here we can see that tetrahedral is going to give us about 110 degrees between the two pairs, the two electron domains. So we have our central atom, and then we're going to form this tetrahedral. It's like a triangle bottomed pyramid here. So we have 3 points on the bottom and then 1 point on top. When we go to 5, we're going to form this pentagonal piece here. So now we have that triangle in the middle, but now we have one above the plane and one below the plane, and we call that trigonal bipyramidal. Okay, now we also have terms like equatorial and axial positions. All right, so axial, top and bottom, equatorial in the middle. When we move to 6 electron domains, we're going to get what we call the octahedral. And so now we have a square in the middle, and then one sticking out of the plane up and one sticking down out of the plane. Now if I rotate this though, assuming that all 6 connections are exactly the same, they're equivalent, then obviously these bond distances would all be the same, and we're down to 90 degrees between each one. All right, so identify for each of the following the number of electron domains, the electron pair geometry. So which domains do we have in NH3 here? So we have a lone pair, and then we have single bonds. All right, so we have 2 types of domains. What will be the geometry? So the basic geometry for this is going to be a tetrahedral. Okay, tetrahedral. How about for water? So for water, we have 2 types of domains. We have the lone pairs, and then we have the 2 bonds. So again, we have 4 domains total, which means our basic shape is going to be a tetrahedral. Now, once we figure out the basic shape, remember there's going to be subsets of shapes as well. So both of these would not be labeled as tetrahedral, or that would start to get confusing. The basic shape based upon domains is the tetrahedral. Now within that, we're going to look at how many bonding pairs do we have and how many single pairs do we have, lone pairs. So for this one, we have a basic shape of tetrahedral, but because we have a lone pair and then 3 bonding pairs, this is going to become trigonal pyramidal. Trigonal pyramidal. And for the water, since we have 2 lone pairs and 2 bonding pairs, that's going to get termed as bent. B-E-N-T, bent. Now, when we move to this third one here, we have 1, 2, 3 lone pairs and then 2 single bonds coming off of this. That's going to be 5 pairs altogether, which if we back up is going to give us our bipyramidal, right? So trigonal bipyramidal. So we have a trigonal bipyramidal, but 2 of these are equivalent and 3 are not, which means this could turn out being linear, or it could be T-shaped or bent, one of those 3. Sorry, it can't be T-shaped because we need a 4th atom. So it's either going to be bent or it's going to be linear. Now, a central atom has 2 lone pair of electrons around it and 2 single bonds to 2 other atoms. What is the electron pair geometry around the central atom? Tetrahedron, pentagon, trigonal bipyramid, square pyramid, or octahedron? So a central atom has two lone pair electrons. So we have a central atom, two lone pair, and two single bonds, two other atoms. What is the electron pair geometry? Well, if we have 4 total domains, that means it's going to be a tetrahedral. All right, what is the electron pair geometry around an atom that has 6 electron domains? What are the angles between the electron pairs? Sketch it in a way that implies the 3-dimensionality of the structure. All right, so what is the electron pair geometry around an atom that has 6 electron domains? Well, that's going to be an octahedron, and it's going to be 90 degrees. Now for sketching these, the easiest way to sketch it, they give us pictures that look like that, but realistically, what you'll see in a lot of textbooks is we'll draw a square for an octahedral, and then we'll draw a point up, and then from below that plane, we'll draw a point down. So the square is in the plane, and you're kind of looking at it like you're looking at the horizon. And then sticking up out of the horizon is this position, and then sticking below it would be that position. Now again, the way they're showing it, you take these lobes and you can kind of draw it out like that. That's kind of insane. And then you can see here's that square that we're drawing in our square model, square planar model, and then there's that position and that position. All right, how many electron domains are there around the central atom in SF4O? And then what is the electron pair geometry for the compound? Okay. So is it 4 tetrahedron, 5 pentagon, 5 trigonal bipyramidal, 4 square pyramid, 6 octahedron. So we have SF4O. So what's it going to look like then? So you know, all those things are going to be linked out like that. Now we could go back to our last chapter, look at how we do our electrons, how we put these structures together, so we can figure out how many electrons are about that sulfur, because that's what's going to matter. If the electrons form another position, then we have 6 domains, and that's going to give us an octahedron. If it doesn't, then it's probably going to either be 5 trigonal bipyramidal or 5 pentagon. I don't think it's going to be pentagon though. That doesn't sound right. We didn't see that name yet. So here we're going to have 6, 12, 40, right? So 40 electrons. So now we've got 8, 16, 24, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right, so that would be all of our electrons being used, which means at this point then, it should be C, trigonal bipyramidal. All right. So shapes involving lone electron pairs. When we start to look at those lone pairs, they take up more space around the central atom. So if you want to think of the lone pairs as being completely negative and they balloon out, it forces all the other bonds to get tighter, right? So that's going to affect the overall geometry. Now, they must be counted though as electron domains. Now, shapes involving multiple bonds, double and triple, for the purpose of molecular geometry, we'll treat as a single electron domain. They're going to be the same as single bonds. So even though it's a double bond, it's going to get treated like it's taking up the area of a single bond between the two atoms. So structures based on 3 electron domains then. If we have 3 electron domains, but there are no non-bonding domains. So in other words, it's going to look something like that. It's going to have 120 degrees. We call that planar triangular. Planar triangular. So remember, if I only have two bonding domains, then I only have two options. Okay, it's going to be linear or it's going to be an atom. Those are your only options. So it's either going to be linear or it's going to be an atom. When I have three bonding domains, we can change it up a little bit. So now maybe I only have two bonding domains and one non-bonding domain. So in other words, now I've got something like this where we've got tin, we get two chlorines, and then we have this big balloon lone pair. Okay, that means we're going to have a nonlinear bent or a V shape. Okay, nonlinear bent or a V shape. And so we'll say either bent or V shape. Typically we're going to say bent. Okay, it's usually bent is the one that's acceptable. Now when we move to 4 electron domains, remember I can have 0 non-bonding. In other words, no lone pairs. That's going to give me my straight tetrahedral. Okay, so that's a tetrahedron. Don't have to do anything to that. Now if I have 3 bonding domains and 1 lone pair, we saw this with our ammonia. So here we have the lone pair sticking up. We have the 3 hydrogens connected to the nitrogen, and we're going to call that a trigonal pyramid. When we have 2 and 2, we saw this with the water, we're going to call that bent. Okay, so far so good, I hope. Now we have 5 electron domains. If you have 5 and 0, then we got our basic trigonal bipyramid. If you have 4 and then 1 lone pair, it's going to look something like that. We're going to call that the seesaw. Okay, distorted tetrahedron or seesaw. And if you're wondering how we get to seesaw, well, flip it on its side, right? So if we have our metal here, and then we have X there, and X there, X here, X here, and then of course our lone pair up there. Now remember, this is coming out at us, that's going away from us. And now you can see as this goes down, that goes up, and that gives us our teeter-totter or our seesaw look. All right. Now remember, you have the axials and the equatorial bonds. That means you have different lengths sometimes. We have 2 atoms in the axial position, 90 degrees to atoms in the equatorial plane, and then you can have 3 atoms in the equatorial position. So 120 degrees between those, right? So there's 120 here going around the circle, but there's only 90 coming from top to the middle to bottom. All right, so where do lone pairs go first? Well, remember you have 120 versus 90. And so we're going to take up the axial positions, and there you can see now we have our seesaw. So we're going to put our lone pair in an equatorial position, which means our axials now will look like that seesaw. Okay. Now if I start to move another one, so remember we have 5 electron domains. So now if we're going to take 3 bonding and 2 non-bonding, it's now going to look like a T. So we'll call that a T shape. And then we have 2 bonding domains with 3 non-bonding domains. Now we have linear. All right, so relative sizes of electron domains. For bonding domains, they're going to be oval in shape. Remember, you have 2 nuclei here that are positive. That's going to keep those electrons sort of flowing in the middle between them, right? Because opposites are attracted to each other. The electron density then will be focused in between the 2 nuclei. For the non-bonding domain, it's more like a bell or a balloon, because the only thing you have is this nucleus keeping those electrons in check, which is going to allow them to spread out and take up even more space. Okay, so the electron density then only has 1 positive nuclei at the end. Now when we move to 6 electron domains, we know we have 6 and 0. We call that an octahedral. Everything looks the same. They give you an example of SF6. If you go to 5 and 0, now remember before we would take out an equatorial position. Now it's not going to matter, because remember that in an octahedral they're all the same. They're all 90 degrees away from each other no matter which angle you take. So we're just going to take the bottom out, and then we're going to call that a square pyramid. All right, so now we have that pyramid with a square base. When we go to 4-2, we're going to take the other end out. So once we take the bottom out, if you call it the bottom, the next thing we're going to do is take the top out. If we take the top out, we're going to call that square planar. All right, so steps used to determine three-dimensional structures. Again, the first thing we'll do is draw out the Lewis structure of the molecule. We don't need to compute the formal charges to necessarily do this. If you have several resonance structures that exist, we're just going to pick one of them and work through the problem. The next thing you want to do is count your electron pair domains, lone pairs and bond pairs around the central atom. Okay, so we'll draw the Lewis structure of the molecule, we'll count out our pairs, then we're going to arrange our electron pairs to minimize repulsion. Okay, so lone pairs, for instance, will require more space. They may slightly distort your angles. In trigonal bipyramidal, lone pairs are going to be equatorial first, then move to axial. In octahedron, the lone pairs are going to be axial, but we do that for the picture, not necessarily because of the chemistry. Okay, it's not going to matter. Now, we name the molecular geometry by position of atoms, considering only the bonding electrons. So your 5 basic shapes, it doesn't matter what type of domains, that's based on just the number of domains. But when you go into your more precise or more accurate naming, then you're going to be looking at just the bonding pairs. So identify each of the following: the number of bonding versus non-bonding domains, the molecular geometry, molecular structure, and now we're going back to these 3 examples that we've already looked at. Okay, so again, when we do ammonia now, we can see that we have the number of bonding versus non-bonding will be 3-to-1. So before it was a tetrahedral, now it's going to be trigonal pyramidal. For the water, we now have 2 bonding, 2 lone pairs. That's going to be bent. And then this one that we left kind of could be this or that. You can see now we're going to take the electrons out of the equatorial first, which means that one is now going to be linear. All right, so what is the molecular geometry of a molecule with 4 single bonds and 2 one-electron pairs attached? Okay, so now what is the molecular geometry of a molecule with 4 single bonds and 2 lone electron pairs attached to the central atom? So you have 6 domains around the central atom, which means you know you're looking at octahedral. But now we're going to remove the axial positions, and so we're going to be left with square planar. So again, you're going to remove the axial positions. For the species ICL5, how many bonding domains and how many non-bonding domains exist? So for the species ICL5, how many bonding domains and how many non-bonding domains exist? Again, you might have to draw that out. Hopefully you come up with 5-1. Right? So again, might need to draw it all out. We get Cl, 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 Cl. Then you count how many electrons you have. Well, we have 6 atoms, each with 7. So we have 42 electrons total, which means when we do our electron count, we know we're going to end up with a lone pair down on the bottom, and that's going to be square pyramidal. Okay. So for the species that you just considered, what is the electron domain geometry? Well, the geometry, remember, that's going to be your basic shape. So the fact that we don't see square pyramidal on here shouldn't bother us. Right, it's going to be an octahedron. And there's our square pyramidal shape that we just drew on the last slide. And of course, that means for the species you just considered ICL5, what is the molecular geometry? And there it is, square pyramidal. Right? All right. So in the next segment, we're going to get into polar molecules. So we're going to talk about those dipole moments again and look at how the geometry is going to influence what that molecule is going to look like. So stay tuned for that.